Hello, everybody! Bom dia, boa noite, senhores. Meu nome é Fábio Teles, estamos aqui começando o nosso PGConf localhost. Como vocês sabem, a gente teve que cancelar o PGConf.Brasil 2020 esse ano. Não foi possível a realização devido à pandemia. As pessoas estão ficando mais em casa e, por uma série de dificuldades, a gente acabou cancelando o PGConf.Brasil 2020. Mas, no lugar disso, a gente resolveu criar um outro evento online, gratuito para todo mundo, mais simples. E a gente vai fazer 6 lives. Estamos começando hoje com o Momjian, que está aqui já com a gente aqui no estúdio. E eu gostaria que vocês... Depois a gente vai postar o link aqui do site, tudo bonitinho. Deixa eu ver aqui, tem o link do nosso site aqui do PGConf Brasil, aqui, onde tem a grade de todas as palestras. Vou pedir para vocês se inscreverem no canal aqui no YouTube, ativar o sininho, né? E acho que vamos começar, né? Para não enrolar muito. Vou chamar a vinheta aqui e depois eu já chamo o Bruce Momjian para falar com a gente, ok? E, senhores, perguntas para quem quiser fazer a pergunta aqui no chat, a gente vai estar trazendo para o Bruce. Quem puder fazer a pergunta em inglês, facilita a vida para o Bruce. Quem não puder, faz em inglês, a gente traduz aqui da hora, tá bom? Vamos lá, pessoal? Bora lá! Hi, Bruce!
Hello, bom dia.
Bom dia. Now, good night. Boa noite.
Boa noite.
Buenas noches. Bruce is one of the most brilliant developers in Postgres. He started at the beginning of PGDG, the group who started to develop the open source project of Postgres. I think most of you know Bruce from other talks, from the groups of Postgres. I will let him talk from himself and start the talk. Welcome, Bruce. Welcome back to Brazil again, one more time. Hope the next time we will see each other here in Brazil.
Yes, that would be wonderful. I was really excited to be coming to Brazil in August. We had that whole conference set up, and then this quarantine happened. I'm certainly very disappointed. It has been too many years since I've been there. I have been meeting Brazilians in a country, so in Germany, Amsterdam, France, there's a bunch of Brazilians who I know from your community who have moved over there, but I have not been to Brazil in too long, and I really would have loved to come down, and hopefully we'll do it next time. It is wonderful to be able to talk to you today online. I've been doing a lot of online conferences. In fact, I put out a blog entry on my website Monday talking about the online conferences that I've been doing. I'm doing this event in an unusual circumstance. I have no electricity, so therefore I'm using a hotspot on my telephone and my mobile phone and the laptop, but it seems to be working. My website, which is actually listed right here on the presentation, is currently not active because the website is in my house. So if you would check on Saturday, the website will be available, but right now and probably tomorrow, there will be no electricity here. So therefore, the website will not be working. But hopefully you'll get a chance on Saturday or later to check out my website. There are the slides for this presentation, slides for over 30 other presentations are there. And there's over 600 blog entries categorized by topic. And I think you'll find some really interesting things here. So again, it is a pleasure to be speaking to you. I wish I was there. I wish I was in Brazil. But this is the next best thing. And again, as soon as travel starts and we have an event down there, I'll be glad to come down. So let's get started with yeah, I'm sorry, Fabio.
Okay, let me put the...
Fabrizio,
Bruce?
sorry. Yes, sir.
Okay, you can start now.
Okay, great. Okay. Okay, great. So, this talk I wrote maybe a year ago, and the reason I liked this talk is because it takes an aspect of Postgres that you don't hear a lot about, but is actually one of the major reasons that Postgres is so popular today. And the basic notion here is the term non-relational. Now, we've all heard of relational databases, right? Relational databases go back to 1970. What is that? Like 50 years ago, right? It's hard to imagine, but we're using technology, the relational model developed by E.F. Codd in 1970. And the amazing thing about this is that this relational model is still being used 50 years later. And why is that true? It's because it allows for very complex data storage to be structured in a way that you can access it very simply with a language which we call SQL. The original language Codd used was not SQL. It was actually a language called Quell, but SQL was developed by IBM, and SQL is the language that we typically use today for relational systems. So we've had relational for 50 years. We've been using it for a whole bunch of cases. We've been using it for order entry and websites and many things. But the relational model that has been around for 15 years is not always ideal. There's a lot of people, particularly in academia, who think that relational is the only way to store data. And that might be true in the educational world, but in the real world, where you have a lot of requirements, relational is not always the best way to store your data. Okay, so let's talk about what is relational storage. So relational storage is basically rows and columns that are organized by tables. You can also is concept of normalization. Normalization basically has a very strong mathematical foundation, and then you join your data together. That's the typical way that you do your data. So what is normalization? What is this sort of term? You might have heard first normal form, second normal form. If you study databases in university, you've heard these terms before. So in data normalization, the relational model says that every column should be atomic, have only one value in each column. Okay? You shouldn't be repeating groups in tables. You should create a separate table for each set of related data, meaning you shouldn't join them together. And you should have a primary key for all your data. Okay, these are, and again, I have some websites there at the bottom that go into this 50-year-old structure of how to store data. But as I said before, first normal form and this relational model doesn't always work well in real world applications. Sometimes query performance suffers if you're having to join too many things together. Queries can become very complex. There is an inflexibility of storage depending on how you store your data. There's sometimes additional overhead and also indexing limitations. And I'll be talking about that, that in a minute. But the bottom line is that first normal form and the relational model works great for most use cases. But there is a significant set of use cases where it doesn't work well. And what I'm going to talk about today are those cases where relational storage, traditional relational storage, following guidelines do not work. And the exciting thing, and the reason I think Postgres has become so popular, is effectively its ability to not only do relational workloads, but to do non-relational workloads. And I'm going to go through 8 examples specifically of workloads where a relational model doesn't work very well, but Postgres, because it can do relational and non-relational together, offers like the best of both worlds. And there's almost very few relational databases that can do both the relational and the non-relational together. Okay. So let me stop now and ask, are there any questions that people have so far? Is that a no? Gentlemen?
Hi, Bruce. No, there are no questions for now.
Very good.
Okay.
Thank you so much. I just wanted to make sure everyone could hear me and everything was clear. Everything seems to be working well.
Just sometimes your connection seems suffering some slowdown, but let's go ahead.
Okay, so why don't you let me know if you want me to turn off my camera, and that would probably fix the problem.
Oh, let's try that, please.
Should we try that? Okay, I'm going to just turn off. I'm sorry about that. I have to, just really weird. Okay.
Now your presentation is gone.
Yeah, I know. I'm back. I did the wrong thing. Okay.
Just a minute.
Okay. So is everyone good?
Okay.
Is it working?
It's working.
Okay. So my camera's off, but you should now not have any lag. Is that better?
Better. Fabrizio, turn off your camera too.
Okay. I'm sorry?
No, go on.
Oh, my camera's still on, isn't it? Hold on. Hold on. Yeah, I'm sorry. Let me turn it off. Hold on. I'm going to stop my screen.
No, Bruce.
Stop my camera.
Yes, your camera now is
there we go.
Is turn it off. And just
Great.
share your screen now, please.
There we go. There we go. How is that? Is that better?
It's okay now.
Everyone's good?
Great.
It's good. Okay. So I'm sorry about the video. I think it's because I'm going through a mobile phone that the video just is a little too much for it. So let's talk about these 8 non-relational storage options. Now, the reason Postgres is so good with non-relational storage is because when it was originally developed in 1986 by Michael Stonebreaker, it was an object relational database. So it had extendability. So effectively all 8 of these options for non-relational storage are part of the extendability of Postgres. Okay. So the first one is arrays. Now you may not even know Postgres supports arrays, but Postgres has supported arrays since 1986 when it was developed. So what is an array? Well, an array is an ability to store more than one value inside of a field. So here I have an employee table with a name and then a certification field column, which has a text, but it also has brackets after it. And when the brackets are there, the brackets indicate that this is an array of text, not just one text field, but an array of them, okay? So as you can see in the second query here, the insert is inserting an employee named Bill, and Bill has 3 certifications for him, okay? The third query, we're selecting all of the columns, and you can see in red that indeed we have 3 certifications, so 3 text values in a single column. Now that's not relational because it's not in normal form, but there are a lot of cases where it's easier to place an array of something than it is to create, value 1, value 2, value 3, value 4. If you've ever seen schemas that just have numbers, right? Because they don't know how many they're going to have, so they just number. Oh, let's just go to 10, right? Not a great system. Much better system is to have something like an array where you can effectively just put as many values as you want. Okay. The last example, last query uses an operator. Now we're going to see this operator quite a bit. It's called the containment operator. And what it says in very concise form is to say, I want the name of the employee where ASCP is a value contained in, or I'm sorry, where certifications contains the ACSP value, right? So I could have a whole bunch of different values in this array. And this is basically saying, take the certification array and tell me if this value appears anywhere in that array. And you're going to see that containment operator over and over and over again in this talk, because containment is one of the major non-relational aspects of Postgres. Now, finally, at the bottom, we have a URL. And the URL there, and again, it doesn't work today. It'll work on Saturday, I hope. That URL, if you want to download the queries I'm using in this slide deck, you can download them from that URL and then run them, and you can see or play with the queries that I've been creating. You can index arrays. Here I'm saying, give me the first element of the certifications array. You can also use unnest, and unnest takes an array and it converts it to rows. So I've taken an array which had 3 values and I've created 3 rows out of it. In the same way, I can do sort of a join. Basically, I'm taking the name and I'm now unnesting in the target list, and now it spills out and it creates 3 rows. The same name is there, but obviously the certifications are now 3 different values. Okay. I can create an array. So here I'm selecting the values from the system tables in relkind, and I can actually use a function called arrayAg, which will convert a set of rows into an array. So unnest converts an array to rows, and arrayAg converts rows to an array. So again, back and forth. And this array capability is used in the Postgres system tables and so forth. So it is fairly popular. Any questions about that?
I want to make one question, Bruce.
So let's talk about the next one. This is a really complicated one. When somebody told me about this, I didn't know what they were talking about. Someone came to me and they said, "Oh, there's this range type, and we're going to add it to Postgres, and it's going to be great." And I'm like, okay. I said, "What does it do?" Well, they said, you know how in a table a lot of times you have like a start time and a stop time, either for an employee or a rental or maybe a minimum maximum or something. You have some kind of range. I said, yeah. And I said, normally they said you put, start as a field and a stop as a field, and they're separate. I said, yeah. I said, well, they said in range types, you start and stop and you put them in one field. And I'm like, well, why is that useful? Right? Like, why? I've done it separately for so long. I don't understand why putting them together is so useful. Okay. So let's see why it is so useful. So looking at the first query, you can see that we create a table called car rental, and we have an ID that's serial, and it's the primary key. And then we have a time span, and this is a special data type. It's called TSTZ range, and that's a sort of acronym or shortening for timestamp with time zone range. What does that mean? That means that this time span field has a start timestamp with time zone and a stop timestamp with time zone in the same field. So looking at the second query, and again, anything in red is where you should be looking, right? Because I know these are big queries. So I tried to make everything you should look at in red. So the second query in red, you can see that I am inserting a start time and a stop time for the rental of this car. That's kind of interesting. Okay. Then in the third query, I'm saying, give me the car rental that contains, remember that containment operator? Give me the car rental that contains that time. And it returns row 1, which is the row I inserted up there at the beginning. Okay. And the last query, if I ask for a range that I don't have, it returns nothing. Okay. So it's kind of interesting. We're using we're using a containment operator to kind of make shorthand. Instead of saying greater than the start and less than the stop, we're basically saying contains this thing. Here's a example. I'm going to create a car rental entry for every day for a 10-year period. So from 2001 to, I think, I guess for 1,000 days. Is that 1,000 days? Let me look. Yeah. So I'm going to create a span from 2001 September to 2010. It's more than 1,000 days. It's, I guess, 3,000 some days. To 2010, 2019. You can see this is right here. So this is the start. This is the start value, and this is the stop value. And I'm going to create a separate row for every day. So 10 years, every day for 10 years. So then I'm going to do a query. I'm going to say, give me the car rental that contains 2007, August 1st, 0801, right? And it shows me, in fact, that entry. Now, notice at the bottom, when I ask for, I go do an explain, I say, tell me if it's using an index. And it says, no, it's going to do a sequential scan across this table. Okay. However, one of the great things about range types is that we have indexing support. So I can say, create index on car rental using a gist index, and I index that particular timestamp with time zone range field, in this case, time span. Okay. And now when I do an explain, it actually uses the index scan to properly index that entry. All right. So I think that's kind of useful. Basically, it's basically taking it and it's using an index where it normally wouldn't be able to do that. That's a great example of something that normally wouldn't be possible, and now is, because we've taken the two fields and we've pushed together. Okay, now are sort of joining them together, and because they're joined together, I can create an index. Not usually you'd have to create one index on the start field and another index on the stop field, and then you'd have to like match them up, right? Because you're using a combined field, you now create an index on just the column. It has both values in it, and it uses just index to find their value really fast. So I think that's exciting. Another exciting thing with these indexes, with this data type, is something called exclusion constraint. So imagine that you want to set up a constraint So nobody ever rents the car in an overlapping fashion. So there's one car, let's say, right? You can't rent the car to two people at the same time. So what this shows me is that I can create an exclusion constraint using the double ampersand there at the bottom, which says I never want overlaps inside of this column. This is actually very hard to do from the client, but because it's supported in the server, you just define this exclusion constraint once, and then it will automatically throw in it, tries to overlap the values from that. Any questions? We're good?
Bruce, I want to make one question. Two guys
Yes,
asked
sir.
here about performance and using index. And you talk about this right now, but I want to know which operators use index and how we know which operators you will use index with these data types.
Yeah, that's a great question. So if you'd like, I can show you another presentation that I have. I have another presentation. Let me just hop out of here if that's okay. Just going to do this, right? You're getting to see my thing here, right? And we go down to desktop, and I'm just going to show you. I'm going to show you. These are all my presentations. And I have a presentation called indexing. Okay. And I'm just going to show you this. So this is another presentation, again, on my website. And it goes through all of this. But it does have some really interesting queries. And the queries are, these are the index types, gin, gist, hash, whatever. And this query, for example, all of the data types that support B-tree. So one of the way Postgres is set up is that the system tables themselves define what indexes, what data types are supported by what indexes. Okay. So in this case, you can see B-tree is quite a big list. This is the Brin type for data warehouse. This is the gin type, which is primarily JSON and full text search, as you can see from this list right here. Okay. And this is the gist support. So you remember I said range type? Here it is right here. So this is showing the gist index supports range types, for text search. It supports circle, box, JSON B, network, and polygon. Is that what you were asking about?
Yeah, that's it. Great job, Bruce. Thank you very much.
Great. And there's also something called SPGist. So again, if you want more detail, I do suggest that you take a look at this presentation. And I think there's a video of me giving it. So in fact, what's interesting, and I'm sorry I can't show you my website, but normally when I give a lecture that's multiple hours, I start with my Postgres Ascent of your data center, which is another talk. I'll just show you what that one looks like, just so you can see. Right here. Where is it? Right here. Okay. So this is the one that I normally start with. Okay. Which talks about extendability. The system tape talks about extensions. It talks about installing languages. It talks about the indexing types. It talks about, adding a whole bunch of stuff. Then it goes into NoSQL and so forth, and data warehouse. Then I talk about the non-relational one, which is the one we're doing now. Okay. And then finally, I talk about the indexing one, the indexing talk, the one I just showed you. So the normal progression, if we had multiple hours, would be to start talking about extendability, talking about the flexibility of Postgres, then talking about non-relational, which is what we're talking about now, and then finally talk about the indexing details. So that's usually if I had multiple hours and we were doing a tutorial, that's usually the progression I would do. And I understand it's a lot hard because you haven't heard the beginning one and you haven't heard the ending one. These is a separate talk, so there's nothing wrong with giving it separately, but there is additional detail available on the website. Are there any more questions?
Bruce.
Just one question here.
Yes, sir.
Bruno asked if the use of JSON is mandatory, or you can use B3 when you use one type or another.
So, if we go back over to indexing, okay, and I'm just gonna pull it up because that's a great question. A lot of people just want to use B-tree for everything. I think that's what the question is. And you can see Postgres supports a lot of indexing for B-tree. But B-tree, and in fact, range-ops is listed as supporting B-tree. Okay? As are point and so forth. But B-tree is really specializes in linear indexing. That means that you're looking at something in one dimension, right? So think of a number line. You have a very small value, right, and a very large value. That's where B-tree works really well. But gist, for example, works much better when you have a lot of duplicates, like full text search or JSON-B. And it also works really well when you have two-dimensional values, so points and ranges. Those are two-dimensional, right? Boxes. Yes, you can use B-tree for a box. How do you index how do you index a point in B-tree? You can index the X value, but then how do you index the Y value? Okay. The way that, and I might go over time. I'm a little worried, but this is the way that gist works. It basically, instead of trying to have everything on one number line like B-tree does, it basically tries to group things in boxes. So it creates ranges in boxes, it creates points in boxes. And instead of trying to do it linearly, look at a lot of points kind of close to each other. Let's put those on one next page, right? And then I have a whole bunch of ranges. I'm going to put those on another next page. So what it is effectively this automatically balancing group of boxes and groupings, so that in B-tree, this would be very inefficient. You couldn't do it. Because if I took all these points, I just indexed them on X, like this point and this point have the same X value, right? But their Y value is completely different. So as you can see for gist, they're in completely different boxes. That's not possible with B-tree. So what I normally tell people, even though it's supported, okay, because it shows range types is supported by B-tree, you probably don't want to use B-tree for these. You probably want to use an index type that's more specialized for a range or for a two-dimensional type. Does that make sense?
Great, Bruce. I think it's okay. It's fine.
In fact, if you look at the bottom, it says B-tree support multi-value types like TX vector and range type is only for complete field equality comparisons. What does that mean? That means if you're trying to match something exactly, then you can use B-tree. But in most cases, when you're doing a search for points or ranges or JSON-B, you're not looking for an exact match, right? Or full text search. You're not looking for an exact match. You're looking for a very complicated, I want to know, is it near this point? Is this point in this box? Is this range? Is this particular time in this range? You're not doing equality comparisons. So in fact, it's good that I said that on the bottom slide. The support is there, but unless you're doing equality, equal, not containment, equal, then you probably don't want to use B-tree. Does that answer the question?
Yes, Bruce, it's okay. You can
Great.
go on.
Great, thank you. Okay. So, number 3, geometry. Geometry, as I've sort of alluded to already, is a combination of an X and a Y. What you can see here is I've taken a dartboard and I've thrown 1,000 darts at it, and I've randomly put the darts on the board. So they're just random points on the dartboard. So you can see there's an X value and a Y value. Okay. You can do some interesting things with Postgres. So what I'm doing here at the top is I'm saying, give me all of the darts which are within a circle of 4 from the center. So this is the center, right? So I'm saying, give me all the points which are in a circle of 4 from the center. So those points are contained in a circle, basically. Okay. But as you can see here at the bottom, when I do an explain, it uses a sequential scan. So it's going to check all 1,000 darts. However, if I create a gist index on my point location, and now I do an explain, you can see that an index is getting used. So this is a great example. Again, B-tree wouldn't work like this, but it will actually use an index to find all the points which are within 4 units from the circle. Even more interesting is you can use limit. So I can say, give me the 2 closest points to the center. This is very hard to do in most relational systems, but Postgres can do it. So you basically say, okay, I've got a center. My center is 50-50. And I want to know the 2 closest points to the center, and it returns that. And not only that, but it uses an index to return it. And that's called nearest neighbor search. Very, very powerful. Any questions about that?
No question, Bruce.
Okay. Yes, sir. The question?
No questions now. You can go on.
No questions?
No questions.
Should we keep going?
Yeah, you can go.
Gentlemen?
Yeah, you can go on, Bruce. It's okay.
Okay, thank you. I'm not going to spend time on this. XML is effectively, a structured language. Postgres can do XML. Here I'm loading in, an XML file of printer information. I can do XPath queries with XML. I can remove arrays from XML. I can convert XML to text. I can do XPath queries with text. I can do non-root queries. I can do unnest. Remember, we saw unnest as part of arrays. Now we're using it for XML. I can do something like give me all the printers that begin with HP, for example. You don't see a whole lot of XML anymore, but you're aware that Postgres does support it. Probably the biggest non-relational feature in Postgres today is JSON. Postgres has 2 JSON data types. The first one is just called JSON. It stores JSON as a text field. It's similar to XML. And of course, there are a lot of support functions for it. So here, I'm loading in an XML JSON file. I'm basically from Muckaroo. It's basically a place where you create JSON data. So I'm loading in a friend table. Now I'm printing the JSON. I can address the JSON by using a dash and a greater than sign or 2 greater than signs. which allow me to access a field inside of the JSON. So if you back up, you can see there's an email, there's a gender, there's a last name, first name, IP address. And notice I just want to look at the email address. So I'm just going to say data dash greater than email. And now it just shows me the email value for that JSON document. Okay. I can concatenate JSON together. I can do here containment operator here at the bottom. So I can either say convert it to text, or I can even say data contains last name of banks. So there at the bottom, we're doing that. I can create an index on JSON, but in this case, because it's not JSON-B, I can only create it on specific fields. I'll show you later why that's better in JSON-B. But right now, we just create on last name. We can create on IP address. I can even do an aggregate here of a JSON field. So again, very flexible. It's sort of like you're taking relational and you're adding JSON to it. Now, JSON-B is really the powerful one. That's the one that most people are using today. It's like JSON, except that Postgres understands the native JavaScript data types like text, number, Boolean, null, and subobject. You can create an index on all the keys and values. I'll show you an example of that. It is stored in compressed format. The keys are sorted, so you can binary search to find them. It does not preserve key order and does not preserve white space, unfortunately. So if you need those, you have to use the ordinary JSON data type. It also retains only the last duplicate. So let's take a look at an example. Here's an example at the top of JSON, and you can see that it has preserved a duplicate name in the JSON document, and on the right it has preserved the space or the colon. If you take a look at the bottom one, you can see that the duplicate name has been removed, and the colon has been removed. The space before the colon, I'm sorry, has been removed. So you see the space is gone, and the name is only Andy because it only takes the last one. So this is sort of a surprising, if you're worried about this kind of thing. But you can index JSON very easily, JSON-B very easily. We create a table, we insert, and now if we want to create an index, instead of creating a gist index, we create a gin index, and we don't index the first name or the last name or the email address. We just index the entire field. And this is only possible with JSON-B. And as you can see here, if I say, give me all the data rows where the last name is Banks, it automatically uses the friend to index here in blue. If I ask for first name of Jane, it uses the same index. If I look for IP address, it uses the same index. So the great thing about this is that when you create this index right here on the field itself, you're creating it on every key and every value, and this is tremendously powerful. Any questions about JSON-B?
Fabricio asks, when don't use NoSQL data? When you don't use Postgres for NoSQL?
So when should you not use Postgres for NoSQL?
Yeah.
Yeah, so I would say if you need to, okay, so I think Postgres is great when you're mixing relational and non-relational together. So imagine you have a product catalog. So you're selling things on the internet, right? And you have certain things of a product are all the same. So every product has a price. Every product has a number. Every product has a name, right? Every product has a manufacturer, right? These are the same for every product. But a lot of products have unique characteristics, like their voltage or the color, or whether they're waterproof, or whether they're rated to go in the rain, or there's a whole bunch of these characteristics that don't fit in relational systems very well. So what people normally do if they're creating a product catalog with Postgres is they're going to create relational columns for the price and the name and the ID and the part number and the manufacturer and so forth. And then they're going to have another field at the end, which is for all the things that didn't fit before. Okay. So Postgres is really great if you're mixing relational and non-relational together. I think Postgres doesn't work well if you just want to store JSON. You don't care about any of the relational features. You don't want transactions, and you want to store JSON on 20 or 50 different servers. And you don't care about transaction consistency. You don't care. In those cases, you're probably better off using Cassandra or Mongo or something that is designed to be multi-server. It's designed not to worry about transactions. It's designed not to worry about queries. And you have a very simple access pattern, okay? There's not a whole lot of applications like that, but there are some where everything is only JSON. You have so much data that you can't fit on a single server. You never want to analyze it, and you just want to dump the data and then get it out. That's not a good use for Postgres. I think Postgres is great when you want to do analytics on it, when the data is going to fit on a single machine, and when you like the transactions, you like the durability, the schemas help you, and that's most workloads. But I think I would say that's the answer. Does that make sense?
Yeah, that's great. We have another question. Let me see.
Yep.
Gustavo asked, which case you use JSON or JSON-B?
Right. So I think I'm going to back up here. I think the only case where you're going to use JSON and not JSON-B is if you have a JSON document and you want to put the whole document into Postgres and you want to take the whole document out of Postgres. You never want to look up fields. You never want to index it. You just want to put the document in and take it out again. Right? I think JSON is great for that. But if you're ever going to want to do analytics on it, if you ever want to pull out fields, if you ever want to do indexing, JSON-B is much better.
Okay. Another one. Bruno asked if JSON-B index everything inside JSON.
Yes. So when I create this index here at the bottom, it's taking that data field and it's actually taking every key and every value and creating a GIN index that references those. Yes. If you look at the other slide deck, I have an example of how it works. So if we just look over here real fast. So here's an example. Where is it? Oh, here. So here's an example of JSON. So I basically insert two people. Okay, this is JSON-B or whatever. And what it does is it says that the active key is in row 1 and row 2. The name is in row 1 and row 2. True is in row 1, row 2. Bill is only in row 1 and Jack is only in row 2. So this is the way the GIN index defines it indexes every key and every value.
Okay. Another question. Fernando is asking about the size of index for JSON-B.
So the JSON-B index is going to be pretty big, but consider that we don't store the key and the value more than once. So notice in this example, the word active is stored once. And then I have a compressed list of matches for that key. The word name and the word true only stored once. And then I have a list of matches for that key. Okay. So if I have a key called name, I don't store name for every row. I store name once, and then I store all the matches for that that
Great.
key or that value. Does that make sense? Yeah.
Another question. Sebastian
Yeah.
is asking for recommended case for JSON-B.
So recommended use case?
Yeah.
Yeah. So I think the example I gave earlier is a good one where you put some of. Remember, I said at the beginning that that relational systems don't always work well, right? And in a typical product catalog, end up creating a whole bunch of columns that mostly are empty, right? So if you have one part that needs to talk about its underwater rating, you need to create a column just for that. What JSON-B is great for is mixing a whole bunch of duplicate data that isn't really structured, and you don't want it to be structured. You just want to you want to sort of attach a JSON-ish. You want to attach this data to a regular row. The best example I heard, and I'm going to go back to this other slide deck because I think it's pretty illustrative. The best example I heard is that administrators have said, if I create a table with a JSON document, I can just index the JSON-B field, and I don't have to worry about indexing anything else. Because no matter what they put in that document, it's indexed. So it gives a lot of flexibility because you don't have to predefine your index. You just basically say anything in that JSON document is going to be indexed. So you don't have to set up a very rigid structure for your relational system. You can just basically put a couple fields and then just put a JSON document for everything and then just index that thing. And then whatever you look up, it's going to be indexed. Does that make sense?
Okay. Another question. Yuri is asking about the storage size of JSON-B versus JSON.
The storage size. Okay. So the storage size of JSON is basically going to use what we call LZ compression. So it's basically going to take a long string and it's going to compress it down. For JSON-B, I think the storage is a little bigger because we can't compress it as well. But if you have a lot of duplicates, then it would compress really well. So I think JSON-B is bigger. I would guess. JSON-B storage is going to be a little bigger. But again, it depends. If you're not going to be indexing everything and you're not going to be looking up anything, then you probably use JSON. But if you want to index it, you want to look up stuff, then JSON-B is much better.
Okay, I think it's okay. Just one more. Bruno, yeah. I think he was having a problem with JSON. In case of dump, data loss is normal. For example, after restoring to a new version of Postgres, you have any case of data loss?
So JSON? What's interesting about all these data types is they're all transactional. So I've never heard of a case where same transaction control integers and text and timestamps, control JSON and full text search and arrays and all this stuff. So there is no shortcuts to this. As far as I know, every data type has the same durability. There should never be any data loss for any of these data types. So I've never heard of a case where JSON data was lost or got corrupted. I've never heard of that.
Okay. One more question about JSON. It's if you can talk about the function JSON path query and indexes.
Right. So JSON path query, is that what you're asking about?
Yeah.
Yeah. So let's look at this query right here. So we're using the containment operator, right? And we're looking up just a simple key and value. Okay. That works for a lot of cases, but there are some cases where you want to do very complicated queries against JSON, where you want to say, I want all the rows that have this top level key and one of these sub keys, and the sub keys have to have values that are in this range of values. So it gets very complicated. So the simple case, and I don't have an example, unfortunately, but the simple case is just containment, key value. Okay. There is a JSON path capability where you can basically create like a query language. Now, is the question about JSON path or JSON path ops?
Okay. Okay.
What was the question? Was it JSON path ops?
He done.
Hey Bruce, we can't hear you.
Yeah.
I'm
You
listening.
can't hear me?
Yeah, now it's okay. It's okay for me, Fabrizio.
Now it's okay, but before there are a lag during his speech.
Is the question about on path ops?
I was hearing okay your answer. Another questions?
Okay, good.
People getting on.
No, I want to know. Yeah, the previous question. What was the previous question? Was it about JSON path or JSON path ops?
No, it's about JSON-B path query function and the
JSON-B path query. Yeah, right.
That's it.
So the point is that you have very complicated. Yeah, so you have a very complicated query, and then you can use the JSON indexes for some of those. I don't know specifically what indexes support what JSON queries. I know certain ones do, certain ones don't, but I don't know the details of that. I'm sorry.
Okay. Let me see. Another question. This is not about JSON-B. Fabiano asked, Postgres has the L3 extension, but is there another way to use Postgres like a graph database?
Okay, so yeah, you're right. We have an extension that does sort of a graph processing, but it really isn't. It doesn't work as well as a graph database. A graph database internally is very different than. So let me back up. So there's 4 types of NoSQL. 4 types. There's the key value. There's the document store. There's the columnar, and then there's the graph database. Okay, so key value, document, columnar, graph. Postgres does key value just fine. Postgres does document just fine. We don't do columnar very well unless you use something like what is it? Citus. And we don't do graph very well. You can do graph, but it's not as good as a graph database. And I don't know when we're going to have something that does as well as a graph database, but you can kind of do it, but it doesn't perform as well, I think, as a native graph database.
But you think with new storages, we will have
new storages,
better.
We're going to have columnar. Yeah. Somebody's already working on something called Z-Store, which is for columnar. I think that's VMware, or is it Pivotal? Pivotal is working on that. And then I assume somebody else will come up with a storage engine for a graph database. Yes.
Okay. Another one, Bruno is asking, you said that all these cases are transactional. Yet
that's right.
Is there a specific parameter that only takes care of this NoSQL case in PostgresConf?
No, it's There's no way to, it's always transactional. You can't change that.
Okay. So I think it's fine. We can go on with your presentation.
Okay. So it's currently at it's currently an hour. Should we take another 15 minutes, or how do you want to do this?
We don't have to end too soon. You can
Because
take your
we were
time.
supposed to go an hour.
No, you
Okay,
can
so I'm
go
going to
on.
go another. I'm going to go another 15 minutes, and we'll finish up. If that's okay with everyone?
That's pretty fine for everybody.
Okay. So there's two more types I want to talk about. One is a row type. You may not be aware of a row type, but a row type allows you to create a type which is a combination of other types. So in this case, I have created a type called driver's license. And I've now created a truck driver table, which which has a license field, and the data type is a row type. So this field has three fields inside of it: state, ID, and valid until. If I do an insert, I can insert the person's name, default value. And now when I go to insert their license number, I have to specify all three fields for that one driver's license field. Okay. I can, if I do a select, you can see the driver's license now appears, as a combined field. I can even, at the bottom there, I can actually look inside the license field and pull out just the state field inside of it. Okay. You see row types used a lot with triggers. You don't see it used too much with applications, because the application, if it gets a row type, it might not know what to do with it because it's just three fields kind of scrunched together. So I don't recommend this all the time, but particularly for things like triggers where you're moving rows around, this is very convenient. Any questions? Okay. So finally, I want to talk about character strings. Now, this is a fairly long section. And again, I want to finish it in 15 minutes because I know it's getting, I want to talk about why character strings are so important in terms of Postgres and non-relational storage. So what I'm going to do in this quiz, I'm going to load some fortune files from FreeBSD. Okay, so we'll just load in some text into Postgres. Okay. And now I'm going to look for all of the fortune fields that have the word underdog. Now, if you look at the first query, I used underdog with a lowercase, doesn't find any. Second one, it finds it. The third one, I actually lowercase the column, and then I compared it so it found either lowercase or uppercase. And you see this a lot in applications where they're trying to match upper and lowercase. Here's another example of if I create an index and I say, look for the lower of underdog. What's surprising is it doesn't use the index. And the reason it doesn't use the index is because instead of comparing line, I'm comparing a function call on line. So the system can't use an index if you haven't indexed on that function call. How do you fix that? You can, in Postgres, you can create what's called an expression index. So here I'm creating an expression index, and I'm indexing not line, but a function call. And now when I use the same function call in a query, it happily uses the index I just created. Here's another example, prefixes. If I'm looking for a prefix, I want to know all of the fortunes that begin with that prefix, MOP. Work just fine. However, it does not use an index. There is a way of fixing that if you use a special index operator called text pattern ops. You can now do a prefix search, and you'll notice at the bottom that it happily did an index scan on that field. Here's another example. I'm doing combining the two. I'm doing a lowercase and then a prefix. Again, does not use an index, but now I can combine my expression index with my text pattern ops, and now I do this and an index is used. So again, combining text pattern ops and expressions indexes. Now that's very simplistic. What about full text search? Full text search is part of Postgres. It is a part of the transactional system, just like JSON, just like range types. It supports prefix searches. It supports whole word searches. It can do and or not searches. It technically converts words to lexemes. It supports 21 different languages. You can remove stop words. You can do synonyms and transformations. So here's an example. If I look at this string, the word I and can are actually stop words. They aren't indexed. The word hard and wait are indexed. Notice in English, hardly becomes hard because it knows that in English, the ly is merely a modifier. So we want to index the base word and it automatically strips that out. I can then say hard and wait. I can say, okay, now I'm back to my query. I say, does this match this? Yes, it does. Does it match softly and wait? No, it doesn't. So again, I'm doing full text search within a transactional database. But there's no index on it. So I create a gin index, okay, with that particular line. Now, if I look for the word panda inside of the query, you can see that it finds one row that has the word panda, and you can see at the bottom that it has used the index I just created to find that word. Again, another example of Postgres indexing capabilities making lookups very quick. Okay. I can do complex things. I can say cat and sleep. Here it's finding one row. I can say cat and sleep or nap, and now I get 2 rows. So again, has a lot of nice features. I can do prefix searches. It is unusual syntax. Give me all of the lines that have a word that begins with zip. It's kind of interesting. All the words with the zip, fills it up. And you can notice that it uses an index for that, which is great. I can also do adjacent letter searches. This is something that full text search typically doesn't do. I'm saying, give me all of the lines that has the word verit somewhere in the text. If it's inside of a word, like here, or at the beginning of a word, like there. Okay. You'll notice, however, that it does not use an index for that. However, we have a thing called PG trigram. You can install it as an extension, as I'm doing right here. Then I create an index on PG trigram. And when I do the verit call, it automatically pulls up the same rows. And you can see it uses the trigram index for that lookup. In general, almost every query that you use has to have some type of index support. And if your database only has B-tree, well, you really can't use a lot of these complex data types. These non-traditional data types typically need a GIN, a GIST index, something sophisticated to allow it to index these non-relational data types, and Postgres does that very well. I can do word prefix searches. I can say, give me all of the lines begin with zip. And again, it uses the trigram for that, using a different syntax. Okay. I can even do similarity searches with trigram. And basically here I'm saying so much for the plan, and it's giving me 3 rows that it thinks are similar to that phrase. I can also do, and it uses an index for that, which is really nice. all of the X created in the section, sort of as a summary, okay? And these are all of the data types supported by the containment operator. So you can see a lot of them we did here before. JSON-B, range types, TS query, okay, circle, arrays, all right? These are all containment operators that we used in different parts of this presentation, and now I'm showing them to you all together, basically, okay? The ones in red are the ones I showed you. The other ones I didn't show you. Actually, range I did. Array, any range I did. Oh, I'm sorry. Is this one I showed you, but not this one, because this is a range versus a range. This is a range versus an element. So this is the one I showed you. So all the red ones I showed you. But again, we have a lot more that are available. Okay. So the big great thing about this is just the ability of Postgres to do some amazing things with non-relational data. Just be aware that non-relational data is not always great. You do too much non-relational data, you end up looking like this squirrel, where you've got kind of stuff all over the place. So non-relational storage is great. Just make sure you're using it at the right times. And don't use it maybe for everything, because some things are better in a relational storage, some things are better in a non-relational storage. The great thing about Postgres is you can do both. So that does end my presentation. I'd be glad to take any questions that people have.
Okay. Any other questions, people? I think no. Actually, we don't have any more questions. I want to thank you so much for your presentation. Hope the power get back soon here.
Thank you.
Let me ask people to subscribe our channel and YouTube. Let me talk about in Portuguese. A gente está aqui, queria agradecer todo mundo aqui que está assistindo com a gente. Quero convidar vocês a se inscreverem no canal. Temos também aqui o Postgres, que é um curso que a gente está querendo montar aqui sobre Postgres para desenvolvedores. Se as pessoas tiverem interesse, podem entrar no link aqui e se inscrever para ter mais informações. E a próxima palestra que a gente vai ter vai ser a do Lucas e do Matheus, falando sobre escalabilidade do Postgres, tá ok? Que vai ser daqui a 2 semanas. E se vocês quiserem ver a grade completa, tem no site do PGConf.Brasil 2020. Poxa, tem gente que me perguntar agora. Agora já foi. Tem mais perguntas surgindo. Deixa eu ver aqui. Okay. Another question, Bruce. We have time? Okay, let me put here. Bruce, any tuning recommendation for Postgres instance or session where you use NoSQL?
I'm sorry, the question is...
if you have any tuning recommendation for Postgres when your session using NoSQL?
A recommendation. I think I answered that before, but let me just say it again. The relational system is great if all your rows are going to be the same, right? But the reason that all these NoSQL systems work really well is when you have non-atomic data like range types, or you have JSON, or you have full text search, where you want to do complex analysis that doesn't really fit in the relational model. So it's not really just JSON and NoSQL. It's a lot of these things that like full text search and range types and arrays and so forth, which really gives you a lot of flexibility. When I use your application for databases, when I didn't have these features, I had to do a lot of really hard work to make something fit into a relational model. The great thing about Postgres is it offers so many features that you can do almost anything, right? You have arrays, you have GIS data, you have full text search, you have JSON, you've got a range that you need indexed. All those things are supported. And there's almost no other database that does that. And I think that's really the great part about it.
Okay, thank you very much, Bruce. Again, hope you can go came to Brazil next year, and we will wait for you at next year. Fabricio, you want to say something?
Thanks a lot, Bruce. A lot. Hope we can meet next year, or maybe this year in another place. And thanks a lot for accept our invitation for this presentation. Thank you.
All right. Thank you, everybody who are watching us. Hope we see you again in the next 2 weeks. So, bye-bye for everyone. Good night.
Good night.
Boa noite.
Boa noite.